Good afternoon, everyone. Today, I will be presenting a PM file system called ODINFS that scales PM performance with a technique we call opportunistic delegation. This is a joint work with my colleagues at EPFL and Virginia Tech. I will start the presentation with a story that motivates the whole project. And the story occurs a short time ago in Silicon Valley. And the story is about May. May is a programmer who builds a file server service for a startup company. And this is the architecture of the file server service May builds. It involves multiple clients and multiple file servers. If we look into each individual file server, it consists of multiple disks and a file system that mounts on top of all the disks to manage files. Client request says, for example, try to retrieve the content of the file is sent to the server, and a server thread handles the request. Concurrent requests from the clients are handled by multiple servers that access the file system and the disk concurrently. So May deploys the file server she built, but there is a problem. The file server is too slow, and May finds that the disks are the performance bottleneck. It has low speed, its access latency is tens to hundreds of microseconds. And furthermore, May finds that the disk performance collapses with concurrent access. So what does May do? May is a storage expert, and she knows about this emerging highly performant storage device, persistent memory, which blurs the boundary between the traditional storage and the memory. PM is especially a great fit for May's purpose because PM has high speed, its access latency is hundreds of nanoseconds, and May reads some document that says PM can preserve performance with concurrent access. So May goes ahead and she replaced the disk with PM and also replaced the file system with a PM-aware file system. During the deployment of PM, May encounters an interesting issue. So specifically, modern machine conforms to the NUMA architecture, where multiple CPU cores and a memory module form a NUMA node. Since PM is memory, there is PM in each NUMA node. However, most of the existing PM file systems are designed to operate on PM of a single NUMA node, and thus they cannot utilize the remote PM. But May wants to first continue with this common setup and see how does the PM perform. So May performed the evaluation with a simple FIO workload, where each thread performs 2 megabyte sequential access in a private file. And the x-axis here is the number of workload threads, and the y-axis here is the I/O throughput. May was expecting that the PM I/O throughput increase as the number of workload threads increase, and then stay at the maximum level. However, in reality, the results shows that PM performance significantly decreased after the number of workload threads exceed a certain threshold. So as a result, we encounter a PM performance anomaly on a single NUMA node setup where excessive concurrent access leads to PM performance collapse. So May is very confused about this result, but fortunately, she has a solution. And the solution is to RAID all the PM across NUMA nodes and then mount the file system on top of the RAID. This not only reduces the degree of concurrent access to PM, but also allows the file system to benefit from the aggregated PM bandwidth across all the NUMA nodes. So May is happy and thinks this can solve the problem. So let's go ahead and see how does PM perform on this multiple NUMA node setup. Here, the red line is the raw PM bandwidth that is aggregated across all the NUMA nodes. And May expect that the RAID setup can achieve a I/O throughput that is close to the raw PM bandwidth. However, the results shows that the RAID setup can only achieve a small portion of the PM bandwidth. And as a result, in this time, we encountered another PM performance anomaly, and in the multiple NUMA node setup, where accessing remote PM is highly inefficient, leading to a low bandwidth utilization rate. So can we help May with a PM file system that overcomes these two above PM performance anomalies and thus maximize PM performance while scale PM performance with concurrent access. And these two design goals form the overarching goal of ODINFS. So in order to design ODINFS, we must first understand the root cause of the performance anomaly. So in a single NUMA node setup, the root cause is excessive concurrent access renders the on-dim caching and the prefetching in PM inefficient. So specifically, to hide the performance gap between CPU and the underlying 3D cross-point media, PM includes on-dim caching and prefetching. When the CPU tries to access a PM block, the prefetcher prefetches the adjacent block into the cache, so that subsequent access can be handled by the cache. However, with excessive concurrent access, it is quite likely that before the PM performs subsequent access, the prefetched blocks are being evicted, and as a result, the subsequent access still needs to go to the 3D cross-point media. And such cache thrashing explains the PM performance drop in this case. So with this, on the single NUMA setup, we obtain a key insight to design a PM file system. A PM file system must control the degree of concurrent access to maximize the PM performance. And we next move to the multiple NUMA node setup. And here, the issue is inefficient remote PM access. To understand the cause, we consider I/O operations in a PM file system. In all cases, a read system call involves a thread that reads from DRAM and writes to PM, while a read system call involves a thread that reads from PM and writes to DRAM. And as a result, the critical components in a PM file system is DRAM, PM, and the thread. And we would like to ask, how does the NUMA placement of these components affect the performance of PM? So based on this, we come up with two setups. In the PM local setup, the access thread and the PM is in one NUMA node, while DRAM is in another NUMA node. And in the PM remote setup, PM is in one NUMA node, and the access thread and DRAM is in another NUMA node. We note that the two setups are performing the same task by copying the data between PM in NUMA node 0 and DRAM in NUMA node 1. And here is the performance result of these two setups with the FIO benchmark we have been using. PM local significantly outperformed PM remote, despite that the two setups are performing the same task. And the cause of this is due to the implementation of directory coherence protocol. So specifically, with Intel machines, the directory coherence information is maintained in memory. When a thread needs to access a remote PM, the system needs to write to PM to update the directory coherence information. The relatively slower PM speed compared to DRAM leads to the slower remote PM access compared to DRAM remote access. And as a result, in this multiple NUMA node setup, we gain another key insight. A PM file system must perform localized PM access to avoid the pronounced PM NUMA impact. So with this, I'm going to present the design of ODINFS. We design ODINFS as an internal PM file system, and we make ODINFS fully POSIX compliant. The design of ODINFS is motivated by the insights we obtained from the performance analysis. Specifically, ODINFS should limit the degree of concurrent access so that it can preserve the maximum PM performance within a single NUMA node. ODINFS should always perform localized PM access. This minimizes the pronounced PM NUMA impact and allows efficient use of remote PM. Furthermore, we design ODINFS to allow applications to benefit from the aggregate PM bandwidth, and we design it in a way so that even the applications on a single NUMA node can benefit from the aggregate PM bandwidth. And the key insight in ODINFS is that these above three design goals can be simultaneously achieved by decoupling PM access from the application threads. So specifically, to perform the decoupling, for each NUMA node, ODINFS creates a fixed set of kernel background threads that we call them delegation threads. Application thread is not allowed to directly access PM. Instead, it must need to figure out which NUMA node the accessed PM block belongs to, and then send the request to one of the delegation threads on that NUMA node. The delegation thread then performs the access on behalf of the application thread. And then it informs the application thread when the access completes. So what is the benefit of this access delegation? First of all, since only the delegation thread can access PM, they effectively act as a central entity to control the PM access. Regardless of the number of application threads, the fixed number of delegation threads ensures that ODINFS always access the PM without crushing PM performance due to excessive concurrent access. Furthermore, since the delegation thread always accesses a PM block local to its NUMA node, as a result, ODINFS always perform localized PM access, and this avoids the performance penalty due to the pronounced PM NUMA impact. To allow ODINFS to efficiently utilize the aggregate PM bandwidth, ODINFS first stripes the data of a file across PM in different NUMA nodes. And then ODINFS performs transparent parallel PM access to utilize the aggregate PM bandwidth. So specifically, when an application issues a read or write system call, ODINFS transparently divides the system call into multiple independent sub-requests. It then sends the sub-request to the corresponding delegation threads. The delegation thread can thus access PM in parallel to serve the system call. And in this way, ODINFS allows an efficient use of the aggregate PM bandwidth. I just present the core design aspects of ODINFS. ODINFS also features a highly scalable PM file system that maximizes concurrent access, minimizing synchronization overhead, while ensuring crash consistency. Integrating the delegation design into a file system requires us to address many non-trivial design challenges. Please refer to the paper for more detail. So with this, I'm going to present the evaluation, and we answer the question, does ODINFS improve I/O performance? We performed the evaluation on a 224-core 8-socket machine, and we used the FIO and the file bench to perform the evaluation. And this slide shows the FIO results, FIO benchmarks we have been using across the paper, and the orange line is ODINFS. As can be seen on the slides, ODINFS significantly improved the PM performance compared to other PM file systems. ODINFS outperforms because it performs controlled concurrent access. It performs localized PM access, and also it parallel PM access to serve system calls, and thus avoid the performance degradation due to the PM performance anomalies. Thanks to the parallel PM access, the application can achieve nearly the maximum PM throughput, even with a small amount of threads. And this is the macro benchmark result of ODINFS. We pick two representative workloads: file server, which is write-intensive one, and web server, which is read-intensive one. And as can be seen from the slides, ODINFS significantly outperforms the second best performant PM file system. So in summary, we have explained why existing PM file systems cannot utilize PM efficiently, because they perform uncontrolled concurrent access, they perform inefficient remote access, and they cannot efficiently leverage the aggregate PM bandwidth. And we present ODINFS. The key insight in ODINFS is to decouple PM access from the application thread to perform controlled, localized, and parallel PM access, and thus maximize and scale PM performance. ODINFS is publicly available here, and I hope you guys enjoy using it. So with that, thank you, and I'm happy to take questions.